We've already looked at piping systems and how to figure out the changes in head for given amounts of flow or vice versa. What we're going to do now is extend that out a little bit to look at what's happening with pumps and piping systems in combination. Because in most practical instances, we don't have a system like this where we've got a reservoir at the top of a hill driving a flow through a pipe. We've usually got a system something more like this, where we've got some water at the bottom of the hill that we'd like to move up to the top of the hill for a useful purpose. Or often a closed loop system like this, where we've got a pump that's driving fluid to circulate in a system. For instance, in a residential hot water heating system or a cooling system. So what we'd like to understand is not just how the flow will move downhill through the pipe under the influence of gravity, but also how we can use pumps to get the flow to go uphill or overcome friction in our practical applications. So in this one, remember, we saw that we would pick 2 points of interest, usually 2 where it's easy to define the conditions. We'd write Bernoulli's equation, Z1 plus P1 over rho g plus V1 squared over 2g. That's the total amount of energy that we had at location 1. Potential energy due to elevation and pressure, and kinetic energy due to the velocity that the flow was moving at. In this case, atmospheric pressure, so no potential energy due to pressure, and the fluid wasn't moving, so no kinetic energy. And all of that energy that we had at location 1 we'll still have at location 2, so Z2 plus P2 over rho g plus V2 squared over 2g. That's the kinetic energy and potential energy at location 2, unless we lost something along the way. And we'll have losses due to friction on the pipe walls and minor losses due to recirculation and secondary flows in things like valves and fittings and so on, entrance losses, exit losses. And that's how we'll do our calculations for our piping system. Now, if we want to put a pump into that system, we'll have exactly the same situation. We'll still pick carefully so that we can easily know what's going on. 2 locations, 1 and 2. Z1 plus P1 over rho g plus V1 squared over 2g equal to Z2 plus P2 over rho g plus V2 squared over 2g. What we had in energy at location 1, we'll still have in energy at location 2, less whatever we lost due to friction and minor losses, exactly the same as we had before up here. But this time we've got a pump. So we're taking the energy that we had at 1, we're adding energy through the head rise across our pump, and that's what we'll have at location 2, plus whatever we lost along the way due to friction and minor losses. So now we're doing some useful work with our pump to overcome the differences due to friction and minor losses and any change in energy state, for instance, to get the water up the hill. Now, much more common in this closed loop, we'll wind up with a flow going around the loop like this through the pump, and we'll pick location 1 here, and that's right there just before we go into the pump. We could pick it anywhere along the way. And we go around the loop, and we're back to location 2. So it's exactly the same idea, except location 1 and location 2 are the same here. So as a result, Z1 plus P1 over rho g plus V1 squared over 2g is equal to Z2 plus P2 over rho g plus V2 squared over 2g. They're both the same point in the circulating system. So instead, we don't have these terms at all. We'll just have that the increase in head across the pump must be equal to the decrease in head due to friction and minor losses as we go around the loop. So what we'd like to be able to do is figure out if we put a given pump in here and have a given length of piping system or a given elevation change in this situation, we'd like to be able to predict how this piping system will interact with this pump to yield a given flow rate, because until we turn this on, we don't know how much flow we're going to get. So we'd like to be able to predict that. So the target of looking at pumps and piping systems in combination is to be able to figure out the flow characteristics that you'll get when you combine the components and operate them in a practical system. Now we know from the practical section on piping systems that the minor losses and the friction losses, these depend on the flow rate. The higher the flow rate, the higher the losses will be. So they depend on the flow rate based on what the piping design looked like. Over here, when we install this pump, this head rise across the pump, it also depends on the flow rate. And it depends on that flow rate based on the pump design considerations. So we're looking over here, the losses due to friction and minor losses will depend on the piping design. The head rise across the pump will depend on the pump design, and the interaction between the two will have to combine to solve for actual operating. So first we'll go back and we'll remind ourselves what's going on the piping side.